Hi guys, welcome back. Good to see you. You're all sitting over there, and I understand. So, maximum likelihood. This is a way of fitting models, and it begins with the idea of I want to have a statistical model that relates what I think is the link between my parameters and my observations. I want to begin with telling you a little bit about the history of this way of thinking, and actually, it's quite old. This idea that um, we use models to estimate things from around us. It begins with something that I'm sure you've noticed, and it's called the moon illusion. And the idea is that there's something interesting happening when you look at the moon um, when it is around time of the sunset. So, suppose you're up here on this earth and you're looking at the moon, and there it is, right about the time that it goes away. You have some estimate of its distance, and it's interesting to think about why is it that the um, moon looks bigger when it is about ready to set as compared to when it's up ahead. So at noontime, you might see the moon, and of course, your distance to the moon at noon is less than the distance at sunset, near sunset, or near the time when the moon is farther away from you. And so it's interesting that we perceive the moon to be larger when in fact its distance is about 1.5% greater when it's near the horizon. So why? Why does the moon look bigger when it is near the horizon? And basically, we don't really know the answer to this. Why the moon looks bigger? But uh, the first person who noticed it and thought about it, as far as I know, is this Arab uh, philosopher. His name was Al-hazen. I think this is like 11th century, and he wrote a book called Book of Optics. And what he said is that, well, the moon looks bigger not because it's actually bigger, but because of our perception. And he said that perception is not in the eyes, but in the brain. And and he thought that perhaps we have some idea of distance when we're looking at the moon. And so it looks bigger, perhaps because we imagine it to be closer to us in one case or farther from. So we have to have an estimate of distance when we see something to have an estimate of its size. And and the idea is that this notion of distance is different when you're looking at the horizon versus looking at up above. And the notion is that when you're looking at the horizon, you have trees, you have buildings, you have things between you and the moon. When you're looking at up above, there's nothing between you and the moon. And so the thought was that perhaps because there are these things between you and the object that you're seeing, the trees and the buildings, it seems like it's really far away. So if it's really far away, your perception of size is going to be influenced by your estimate of distance. So if it looks the same, if you take a picture of it with your phone, you will see that it's actually, of course, smaller when it is at the horizon because it's farther away from you. But your perception of it is that it's larger, perhaps because you believe it to be somehow farther away than it is straight up ahead of you, straight above you. So your perception of size is being influenced by your estimate of distance, and that you view this distance to the moon at sunset to be much larger than it is when it is up ahead. So this was a hypothesis. Of course, we don't really know if that's true. But this was also uh, picked up many centuries later by a famous German philosopher. You've heard of him, Immanuel Kant. And he wrote a book called Critique of Pure Reason. And then he said that perception is a result of two things. What the brain believes and what the sensors tell the brain. This was the notion of having a model, a prior, with which you're going to use to understand what it is that your sensors are telling you. Um, I'll give you a quote from that book. He says, "The understanding can intuit nothing. The sensors can think nothing. The understanding meaning our priors. The sensors can think nothing. Only through their union can knowledge arise." And so this was the idea that we have our perception fundamentally dependent on our models that we use to understand what's going on. So I want to now give you an example of this in a more recent notion. So I'm going to give you an example of a disorder of perception. And I'm going to go tell you about this patient RW. He suffered from a stroke in the parietal lobe. And what his problem was visual motion. So consider the following scene. Suppose that you're looking at somebody walking in a park, and here's this person, and they're going to be walking this way, and you're going to be following this person. Now, what happens is that as you're following this person, of course, your eyes are going to be looking at this person, and as the person walks over there, your eyes are going to move to this location. So the image of the person remains on your fovea. What happens is that on your eyes, what you see is the person remaining still, but the trees going backwards. Does that make sense? That's what your eyes are telling you. If you just were looking at what's on your eyes, the image would be this person stays still, the trees are moving backwards. And of course, that's not what you perceive. You perceive the person moving forward and trees standing still. That's kind of interesting, huh? So your camera is moving with the person. The person stays still, the trees move backwards, but you perceive it to be otherwise. You perceive it that you are observing somebody walking, but the trees are standing still. Okay. So this patient had the problem that was like this. So he would describe going to the park, watching somebody do this, and then as they watched, they got what's called vertigo, which is dizzying spell. And they got a spinning sensation. So they as he watched this individual walk, he was perceiving indeed the trees going backwards, not the person walking forward. And this would cause great constraint in him. He would get dizzy. And this is why he went to see the doctors, and they noticed that he had this lesion. So the idea is that as you move your eyes, so you're sending the commands to your eyes to move, you expect the image to shift backwards. And if that's what it does, then that's what you expected. So you don't perceive the trees as going backwards when you move your eyes because you generated the commands that moved your eye. And that's very different than if you did this. If you did this to your eye, if you pushed your eye with your own hand, what you would see is, image wobbling. But of course, you move your eyes all the time and you don't see the world wobbling. So this illustrates that we have parts in our brain that are listening to the commands that we're sending and expecting changes to occur in the sensors. And then when the feedback comes from the sensors, we perceive the world based on not just what the sensors told us, but what we were expecting. And the idea is that our observations are combined with some prediction, and then together they provide us with an understanding of what actually happened. Okay, so do you have any questions about this? All right. So we're going to talk about how we're going to build observations and how we're going to combine what we observe with what we predicted. And the statistical method to combine these two pieces of information has to do with our uncertainty. So we have a model of the world. We expect things to happen in a certain way. And then we're going to actually measure the things that actually happen. The sensors tell us. And then we're going to combine these two things. And the way to do it is to combine it via some measure of uncertainty, some weighing that says, I not only believe in something, this is the strength with which I believe it. So I'm going to begin to tell you about how we're going to describe uncertainties about beliefs, and then how we're going to use that to combine things. So let's begin with thinking about the concept of maximum likelihood. Maximum likelihood is this basically the idea that you have a model that has some parameters, you make some observation, and then you want to find the parameters in such a way that it maximizes the probability of your observation. So you have data, you have a model that says how your data was generated. That's called a generative model. And then you say, okay, my model is a statistical model that describes how my parameters are related to what I'm observing. Now, what I want to do is to maximize the probability of what I'm observing by finding the parameters that best fit what I'm observing. So one begins with a generative model. It says, how is this data generated that I'm seeing? And that is the description of this mathematical model that describes the process of generation. So, for example, we've been looking at things called a linear regression. So in linear regression, you have two things that you can observe: this input X and this output Y. And I'm writing them using this graph structure that says X and Y were both measured. And then there's this parameter W that we're trying to estimate. But what we're observing, Y, this parameter, this vector or scalar Y, depends on two things: X, which was given to us, W, which wasn't. And we have to estimate. So this is a diagram that describes relationships between variables, and it's describing conditional probabilities. That there's a probability of Y given X and W. So as X and W vary, Y changes. Now we can observe X, but we don't know Y. And so, sorry, we don't know W. And so we want to find a way to maximize it. So let's begin with a generative model, which says, what's the statistical relationship between these things? Well, a simple way to think about it is that, well, this is a normal distribution. So if you had X, if you had given me X, I would say, all right, multiply X with W, that would be the mean of your distribution. And then there's some variance, sigma squared, that describes the variance of your distribution. So this is a linear regression model. It says the Y that you're observing is related to X using this parameter W, and it has a variance sigma squared. So this says the observation Y of n is W transpose X of n plus this noise term epsilon, where epsilon is normally distributed with mean zero and variance sigma squared. Okay, so that's the probability of X. Sorry, that's the probability of Y given X. And so we can write this, if it's a normal distribution, we can write this mathematically. It looks like this. There's a normal distribution with mean W transpose X and variance sigma squared. So that's my conditional probability. This is called a likelihood. Why is it called a likelihood? Because it says, what's the likelihood of observing Y? What's the observation that you made? What's the probability that you would observe something like this, given that I gave you X and you had some parameter W that you had estimated? Well, that probability is this Gaussian, which describes the likelihood of observing some measurement Y. So maximum likelihood begins with a hypothesis regarding a probabilistic model that relates things you can measure to things you want to estimate. And then this is the first step. And then part two of it is you find the parameters that maximize the likelihood of observing what you measured in your data. Okay. So, okay, what's the likelihood of observing my data? So I've been given some data, X and Y. This is my data. So I want to now write this as a probabilistic model. I believe that my data was generated by this model, which means that the probability of my data, the likelihood of my model, so the probability of Y1, Yn, observing this specific sequence of Ys that I was given that I had X1 and W, this probability is called the likelihood. And if each of my observations is independent of every other observation, that's just a multiplication of the individual likelihoods. That's the probability of Y of N given which is just a multiplication of those Gaussians. Well, we can write it down. So let's see what it begins. It's 1 over 2 pi sigma squared raised to the n. This will be a sum. This would be the likelihood of observing the specific Ys that I had. So the maximum likelihood would be maximize this multiplying of all these exponentials, find the W that maximizes that. And we'll do that. Okay, so let's do some simpler problems before we get to multiplication of these Gaussians. So let's do something simple. So let's try with something that's a uniform distribution. Suppose I tell you the data that I've given you is a uniform distribution. It comes from a uniform distribution. Then that means that there's some range over where this data exists. Let's say that's from 0 to A. I tell you that the data that I give you comes from a uniform distribution. I don't know A, but I know that Y belongs to this range. And it's a uniform distribution. So what that means is that the probability of Y I given A is going to be 1 over A. That's what a uniform distribution is. If Y belongs to this range and 0 otherwise. So suppose I gave you a bunch of data from, and you plot it on that scale. So maybe you have some data here like this, something like this. And I ask you, okay, this comes from I believe this comes from a uniform distribution. And you tell me, what is A? What's your guess?
The rightmost value.
Yeah, the largest value, right? Why isn't it the largest value plus 1?
It reduces the probability. It adds like another term that's going to be.
Okay, why isn't it less than that?
Then you have data that's impossible.
Good. So let's do that mathematically. Very good. All of that is the case. Okay, so that's our likelihood. The likelihood of seeing any data point Y is 1 over A, unless A is smaller than the largest data point. So the likelihood of the parameter A is just going to be the multiplication of these probabilities. Probability of I is equal to 1 to, let's say, n data points, which is 1 over A to the n, right? That's when I multiply it all together. So, okay, so I want to find A that maximizes the likelihood of A. Okay, so what's the largest A that I can find? Well, it's going to be A has to be bigger than equal to maximum of my data, the largest value of my data. And obviously, for that to be the case, the best that I can do is to set this equal to the maximum value. If it's any bigger than that, then my likelihood becomes smaller than it needs to be, is what you said. And if it's smaller than that, then the likelihood becomes 0, because I have a data point that's larger than A. Does that make sense? So I maximize the likelihood. Okay. Let's do another one. Let's do a different distribution. Let's do an exponential distribution. So suppose I give you some data and I say that it comes from an exponential distribution. What's an exponential distribution? So there's this data here, Y, and you plot it and you sort of looks like this. That's an exponential distribution. This is P of Y, 0 to some value. So P of Y given A, your model says it's this. That's an exponential distribution. Okay, so I've been giving you some data. I say, what is A? What is the parameter A that describes this distribution? So you say, okay, well, let me find the likelihood. So what's the probability of Y1, Y2, Yn given A? That's a multiplication of I is equal to 1 to n of each one of my little probabilities, 1 over A, which is equal to 1 over A raised to the power n times an exponential of a sum. Okay, so I want to find A that maximizes this likelihood. That's my likelihood. So instead of maximizing this, I'm going to maximize the log of my likelihood. Why? Why can I do that? Why can I use the log of this rather than the function itself? Right. So as long as I maximize any function that's monotonically increasing with this function, that's good enough. You don't want a function that goes up and down because that doesn't make sense to maximize it. But this will increase with the function itself. It's just a log function. And of course, it has a feature of being easy to find derivatives for. So, okay, I want to find the log of my likelihood. So this is my likelihood. All right. So I have 1 over A to the n. That's a log. I want to find the log of that. So that's A to the minus n log of a to the minus n is minus n log of a. I'm going to use natural log because we have an exponential. So let me just change this into natural log. And then I have this 1 over a to the n multiplied by an exponential. So log of a times b is log of a plus log of b. So this becomes minus 1 over a sum of y sub I. All right, so I want to find a that maximizes this. What I'm going to do is I'm going to find the derivative of this log with respect to a. And derivative of a log of something is 1 over that something times the derivative of the inside of the log. So I have minus n times log of a. So the derivative of that is minus n 1 over a plus I have this minus 1 over a. I want to find this derivative. That's a to the minus 2, a to the minus 1. So I get plus a to the squared times sum of yi. And okay, so I found this derivative. And the place where things are going to get maximized is when this is going to be 0. So I solve for that and I get a maximum likelihood is 1 over n sum of data. This is the parameter that is the maximum likelihood estimate of the distribution that we were looking for. Good. Okay. Any questions about this? What do we do? All right, let's do a normal distribution. All right, so in a normal distribution, I have two parameters. I have a mean and I have a variance. So there, the probability of y given mean and variance. That's what I'm interested in, these two parameters. And that's equal to, if it's a scalar, 2 pi sigma squared square root times the exponential minus 1/2 y minus the mean squared. So this is my model of how my data was generated. I've been given some data. I want to find this mean and this variance, and I'm going to use maximum likelihood to find those parameters. So here what I have two parameters, mu and sigma. They generated my data y of my normal distribution. So the likelihood of these parameters, mean and variance, is the multiplication of my Gaussians. So let's multiply them out. So let's say I have n data points. Yeah. Thank you. Thank you for that. Okay, so let's multiply. Let's see what the likelihood looks like. So this is going to be multiplication of all of these guys over the over my data. So if I were to multiply them, I'm going to get something like this: 2 pi sigma squared n over 2. Okay, so here's my likelihood, multiplication of all those Gaussians. Now I'm going to find the log of my likelihood. So look at the first term. So the first term is 1 over this quantity raised to the power of n over 2. So that's that quantity raised to the power of minus n over 2. So I get a minus n over 2, then the log of 2 pi sigma squared. Then I have the quantity inside the exponential, 1/2 sigma squared times the sum mu squared. Okay, so this we can simplify this just a little bit. That first term becomes minus n over 2 log of 2 pi plus 2 log of sigma. Okay, now we want to find the parameter mu, the mean of my distribution. I find the derivative of the log of the likelihood with respect to mu. That's the second term. So that I have the squared sum of these squares. What I do is I find the derivative of each element. Something squared, this derivative is 2 times the thing inside of it, so that this is minus 1 over sigma squared. 2 cancels out. Sum of yi minus mu times the derivative of what's inside, minus 1. With respect to mu, set that equal to 0. So mu, maximum likelihood, is what you're familiar with, the mean of your data. All right, let's find the variance. So let's find the derivative of the log with respect to sigma. Sigma is the standard deviation. See, what do we get? So the first term, I have minus n over 2 times 2 times log of sigma. That's 1 over sigma, its derivative, minus, then I have that sum that has 1 over 2 sigma squared in it. So I get 1 over sigma cubed times the sum squared. Set that equal to 0. Solve for sigma. I have a sigma and a sigma cubed. I get rid of one of those guys, and I get the maximum likelihood to be 1 over n, sum of each data point minus the mean squared. Okay, so this is the two familiar equations I'm sure you've seen. I have the mean equation and I have the variance equation. All right, so when you look in papers, when you read scientific papers, you sometimes see something called standard error of the mean. And I wonder if you've ever thought, what does that mean? What's an SEM? Surely you've seen it. Yeah.
The point is typically from like an average point.
So it's an error bar people plot. And do you know how they calculate it? Yeah. Yes, that's very good. You're estimating your confidence of the mean. And that's somehow related to the variance of the data. So I want to show you what that is. Okay. So SEM. Why is it that people don't plot the variance of the data, but they plot something called SEM? What does that mean? And I want to give you the intuition about what that means. So SEM is a measure of your confidence about the variable that you call mean. So variance of mu ML is what's the meaning of SEM. So what is this variance? Well, okay, what is mu? Here was a mu, right? This is our mu. So what's the variance of that? It's 1 over n squared, sum of variance of each of these elements. What's the variance of each of those elements? That's 1 over n squared, sum of sigma squared, maximum likelihood estimate of it, which is 1 over n sigma squared. So I have n of the sigma squares that I'm adding up. So when I add them all up, divided by n squared, I get this. So I get sigma squared divided by n. That's the variance of my mean. That means that my uncertainty about the mean as measured by its variance is related to the variance of my data divided by n. Okay, so what does that mean? So SEM is the standard deviation of the variance of the mean. That's sigma ml divided by square root of n. And in this way, you see that as n increases, that means as the number of data points that you have increases, SEM of the mean decreases. So your confidence about what it is that you're calling the mean gets better the more data you have. So that's what SEM is. It's your measure of uncertainty about the mean that you're plotting. Error bars are measures of uncertainty. And in the case of a Gaussian distribution, the relationship between the error bar and the number of data points is one where as the number of data points increase, your SEM goes down as the square root of that number of data points. Yeah, does that make sense? So I remember, being with you guys, reading papers, and I remember looking at that. I said, well, I always wondered, like, why is it? Are they like trying to make the data look better by dividing by the square root of n? Why is the variance being divided by the square root of n? And I finally realized, oh, this actually makes sense. That is your uncertainty about the mean. All right. Okay, any questions about that?
Often in neuroscience, they'll plot average firing rate over time.
So yeah.
Average a raster at each time point. Does it make sense to take the standard deviation of a raster like that, ones and zeros?
So in some ways, no, because the time series is probably not independent. So at any time n is probably not independent of n-1, and we just saw that all of the stuff that I did is based on this concept of independence. But then if you want to have it all depends on the model that you use, right? But when somebody does SEM, like I showed you, they're making implicit assumption about IID and a normal distribution of the data, right? Because if it's a different, if it's an exponential distribution, then its variance is definitely not what I showed you. Okay. All right. So next topic. Let's now go to our regression problem. So in our regression problem, we are given X, we measure Y, and there's this W we're trying to estimate. And our model is that Y is W transpose X plus epsilon, where epsilon is our noise, and it has mean 0 variance sigma squared. Okay, so let's write the probability distribution of Y, the data that we have. What is the probability distribution of Y? Well, if epsilon is a normally distributed variable, then so is Y. This is going to be a normally distributed variable with mean. What is the mean of Y in this equation? So if I give you, if I give you this equation, I say, I'm going to give you some data. What is the mean value of Y? Well, of course, the mean value of Y is the mean value of that equation. What's the expected value of the right side of this equation? No, W transpose X, right? So the mean of the right side of the equation is just W, because epsilon is mean 0, right? Okay, what's the variance of the right side of the equation? No. And I'll tell you why, but it's not sigma squared. Because X is a random variable, right? So then it's W transpose variance of X, W plus sigma squared. So why is it this? Because remember, P of Y is probability of your observation. And of course, if X is varying a lot, well, so is Y. Right? So the variance of what you observe depends on the variance of the X that was there. Does that make sense? That's P of y. However, if I asked you, write P of y given x, then that's a normal distribution with the same mean, but now what is the variance? Now it's sigma squared. Why? Because x is fixed. X is not a random variable anymore. Okay. Is that clear? Is that clear why? So we're finding the expected value and variance of the right side of the equation. And that's just, this is algebra of random variables. All right. So likelihood. What are we going to try to do? In maximum likelihood, we maximize the likelihood of the observation. So this is a likelihood. Not P of y, but P of y given x. So we're going to maximize the joint probability of the data. So what's our data? I have y1, yn, given x1, xn, and wn sigma squared. That's my likelihood. So let's write that down. So this is equal to the multiplication of 1 over 2 pi sigma squared 1/2 exponential minus 1 over 2 sigma squared is equal to this is my likelihood. Find the log of my likelihood. Natural log of it. So let's look at the first term. Minus n over 2 log of 2 pi sigma squared plus the term inside the exponential. So that's minus 1 over 2 sigma squared times that sum. Okay. And of course, you notice that this, when we were doing linear algebra representation of our error, this is just y minus xw transpose y minus xw. That's just the sum of the squared errors. So this is equal to this first term minus 1 over 2 sigma squared Okay. And you know how to find the derivative of this with respect to W. That's set that equal to 0, and I get my normal equation. That's the maximum likelihood estimate. The normal equation is assuming that my data was generated via a linear system that has a Gaussian noise. And that's how I get the maximum likelihood estimate. What about my variance parameter? And I get maximum likelihood estimate of variance is the average difference between each data point and the mean. that I expect from it. So these are this equation we've seen before. This gives us the maximum likelihood estimate of the variance because we're assuming a Gaussian relationship between our data, that X and observation Y. Okay. Now let's consider a more interesting problem. Suppose that you have two measurements, YA and YB, and you believe they come from the same X. And to give an estimate, to give you a rationale behind this, is that we have multiple sensors in our body. We have our eyes, we have our, our hands that can touch things. And so when I go to, when I see this little cup here, I can feel it, I can get a sense of its width, but I also see it. I have a sense of its width because of vision. So I have multiple sensors that tell me the same thing, how wide this is, right? To give you another example, I call this the hiking in the woods problem. Suppose that you're going to go to a really harsh location, Antarctica, and you're going to be hiking there, and you don't want to get lost. So what you do is that you make sure that you have access to two independent sources of GPS. So European Union satellites and Elon Musk satellites, two separate groups. And each of them is going to tell you something about your location. Y is a two-dimensional variable. It's your position on this planet Earth. And YA comes from one device, YB comes from another device. So what you measure is this two-dimensional thing with one device and another two-dimensional thing in the other device. Okay, now I want to talk about how do I combine these two pieces of information so I can estimate X, my actual location. Does that make sense? So think about how you would do this problem. So you must have some model that tells you the confidence that you have in each of these measurements. So you have to have some model that says which satellite system is better in estimating my position. That is related to the noise that you assume in your measurement. So let's write that down. So you measure something. This is called the GPS problem. So you measure something Y that's made up of YA and YB. This is a 4x1 vector. Does that make sense so far? One location from one system A, one location from system B. And you have a model that says, well, this thing that I measure is related to where I am, plus some noise. So what are these variables here? Y is a 4x1 vector. X is my actual position. That's a 2x1 vector. So C here must be a 4x2 vector. Epsilon is the noise that I have. I have measurements Y, that's a 4x1, so my noise is a 4x1 as well. So the noise is telling me things noisy in X direction and Y direction, latitude and longitude. Okay, so I believe that on average, these satellites are unbiased. Therefore, I'm going to say C is made up of two identity matrices, each a 2x2. So I don't have any reason to believe that Elon Musk satellites and the European Union satellites are biased. So in general, I'm going to set C to be identity matrix. So therefore, the expected value of each of these variables is going to be the truth. So on average, they're going to tell me the true location. Okay, but epsilon might be such that it is different in these two. Maybe Musk satellites, maybe they have many more of them or better coverage of them of where I am. So I'm going to say epsilon is going to be a normal with mean 0 and variance R, where R now, so let's think about what's the size of R. So R is the variance of this 4x1 vector. So what is R? What's the size of R?
4x4.
4x4. There's an RA, there's an RB, and there's zeros here. This is a 4x4. Each is a 2x2. This whole thing is a 4x4. And I put the off-diagonal terms to be 0 because I believe that they're separate satellites. They don't have any interactions with each other. So the covariances are set to be 0. Does that make sense? So when I put 0 there, I don't mean actual zero. It's a 2 by 2 of zeros, right? Because this is a 4 by 4 matrix. And RA and RB is each of them is a 2 by 2. So my first question was, what is the size of R? And you answered it's a 4 by 4. Why? Because epsilon is a 4 by 1 vector. So therefore, its variance, covariance, is going to be a square matrix of size 4 by 4. Because epsilon is a 4 by 1. So therefore, its variance is a 4 by 4. All right. So now I want to show you how do I find the maximum likelihood location that I'm in, depending on RA and RB. So if you think about this problem, I wanted you to have a sense of how the solution is going to look like. But before we get there, let's just think about it. So I'm going to measure RA and I'm going to measure RB, and I'm going to somehow combine them. How should I combine them if I know RA and RB? If I know the noises in my measurements, how should I combine my measurements, YA, YB? How should I weigh them? Should I average them? Or should I weigh them by the variances? It's always the second part, right? No matter whatever question they ask you, usually the second part. Okay, so you should weigh them. But how should you weigh them? So RA and RB are variants, which are noises that are inherent in my measurements, right? So basically, those are your uncertainties. So you're going to be more uncertain in the satellite system that's more noisy, has greater variance. So you should downweigh that particular measurement. Does that make sense? Okay, so that's going to be the answer that we're going to find. So let's actually show that's the case. So, okay, let's go back to our model. So here's our model. Let's write down what's P of Y. It's a normal distribution with mean Cx and variance C, variance of X, C transpose plus R. Probability of Y given X, that's my likelihood. That's a normal distribution with mean Cx and variance R. Okay, so probability of Y given X is, this is a multidimensional Gaussian now. The size of the number of dimensions is 4 because Y is a 4-dimensional vector. So I have 1 over 2 pi raised to the 4 times the determinant of R raised to the 1/2 . So the probability, of course, is just a number, and it's equal to this multidimensional representation of a Gaussian. Y is a 4 by 1 vector, R is a 4 by 4, and so forth. So this is how we write the likelihood. This is the likelihood function. So now I want to find the maximum. I want to find X that maximizes the likelihood of Y. Find X that maximizes this likelihood. So I find the log of it, log of this likelihood. Let's see, what do I get? I get minus 1/2 times the log of 2 pi to the 4 plus log of the determinant of my variance covariance matrix of R plus what's inside the exponential. That's a negative, so this is 1/2 y minus cx transpose R minus 1 y minus cx. Okay, so that's my log of the likelihood. Then I want to find the X that maximizes this. So I find the derivative of the log with respect to X. And this term on the right, we've done this before. This is a weighted mean squared. So the weighting is by minus R1. This is going to be 1/2 of minus 2 C transpose R minus 1 Y plus 2 C transpose R minus 1 CX. Set that equal to 0. Solve for X, and I get the maximum likelihood estimate of X. is C transpose R minus 1 C minus 1 C transpose R minus 1 Y. All right, so that's just some algebraic representation. Well, what does it mean? Let's simplify this and understand what does it mean. So remember, R was our variance covariance. This was RA and RB. It's a 4x4 matrix. So then R minus 1 is RA minus 1, 0, 0, RB minus 1. That's what R minus 1 is. And remember, C was this 4x2 matrix, identity 2x2, identity 2x2. So let's multiply these out so we understand the meaning of this equation here, which is what I'm after. All right, so let's see, what is C transpose R minus 1? That's this matrix 2x2, 2x2 times R minus 1. So that's going to be this matrix. And then C transpose R minus 1 C, that's just going to be the sum of these inverses. So then my maximum likelihood is the sum of my variances inverted multiplied by the weighted sum of my measurements. This is my mean of the estimates. Look what I'm doing here. So I am weighing my measurement by the inverse of its noise, weighing my measurement by the inverse of its noise, and then normalizing it by the sum of those noises. So this means that whichever input had the least noise is going to get weighed more. I'm going to rely more on it. So, which is our intuition, right? Basically, your measurements should be weighted more by the one that had less noise. Your model said had least noise. So this is your maximum likelihood estimate of where you are. However, we also have a measure of my uncertainty. So this is my estimate of where I am, but how certain am I that I'm that location? That's the variance of my maximum likelihood estimate, given that I'm at some location X. So just like when I plot the mean, I can plot error bars around it. I can also estimate how certain I am about where I am. So I find the maximum likelihood estimate of X, and I can tell you how certain are you about this guess. And what is that? That's the variance of my maximum likelihood estimate. So this is this equation here, the variance of this equation. Let's write that down. So the variance of that equation is variance of the first term. The only random variable there is y. Y is your random variable. So the variance of this equation is that first term times the variance of y times the first term transpose. And so what is the variance of y given x? Variance of y given x is this term. Variance of y given x is this term, r. So let's write this down. So I want to know the variance of XML, maximum likelihood estimate. That is C transpose R minus 1, C inverse, C transpose R minus 1 times the variance of Y given X times that first term, its transpose. So it's going to be R minus 1, C transpose R minus 1, C minus 1 quantity transpose. All right, so variance of y given x is r. This is r. So that obviously cancels out with r minus 1. The variance of my maximum likelihood estimate is going to be C transpose r minus 1, C minus 1, C transpose r minus 1, C times C transpose r minus 1, C minus transpose. Okay, so the first two terms cancel, I get C transpose R minus 1, C minus 1 transpose of this. So the variance is a symmetric matrix, so we can get rid of the transpose. So then I get variance of my maximum likelihood estimate given X is C transpose R minus 1C minus 1. This is my uncertainty for my estimate XML. So I made an estimate that says, I think I'm here, and I can tell you how certain I am about my estimate. There is this variance. So what this means is that the variance of my estimate given X is the sum inverse, which is smaller than RA and RB, which is saying the following. So if one satellite tells you you're here, and here's the variance of it, another satellite tells you you're here, and here's the variance of it. So this is YA, this is YB. When you combine them, you end up with something like here, not in between them, because look, the variances are large here, but smaller here. Yeah, go ahead.
Or calculating the variance of XML.
Yeah.
Why do you variance of XML given X, even though we don't know the true X?
Well, because in maximum likelihood, we're maximizing the likelihood. Likelihood is the conditional probability. And so when I find XML, that's relying on the conditional probability. That's why. Okay, so now the point that I want to make is that each measure comes with its variance. So YA has, look, the way I drew it here. It says that, I have more confidence along this angle, so along this direction, I have more confidence than along this direction. Similarly here, I have more confidence along here than along here, right? That's what those variances mean. So when I combine them, I get a new position, and I say maybe this is the combination here, and I'm going to get some uncertainty about it. And my variance is smaller than either RA or RB. It's because of this. So by combining two pieces of information, I am more certain than if I just had one piece of information. That's what that means. So you always are gaining information when you add to it another sensor. Even though it has great amount of noise, when you combine the two, the total variance that you have, the uncertainty that you have about your estimate is reduced. This is why two sensors are better than one. All right. Let me end with a paper that used this idea to say something interesting about the brain. Remember that I was describing to you this idea that I'm going to pick up this cup here, and this cup has a width that I can feel with my fingers, and I can see with my eyes. And so I have two sensors. And so in a paper written by Ernst and Banks in 2002 in Nature, they asked, does the brain combine two pieces of information, vision and haptics, in a maximum likelihood way? So what's the idea here? The idea is that you want to present an object. This would be a device that you can feel the width of the object, and a monitor where you can see the size of the object. And now you're going to be asked questions about what is the actual width of this object. Now, if you think about it, your sensors here in your hand have a certain amount of noise. And what you can see with your eyes, that's a certain amount of noise as well. You're probably much better in sensing objects with your eyes than it is with your hands. Unless if you're, visually impaired, which you may be much better with your fingers than you are with your eyes. But nevertheless, you have noisy sensors. Your brain gets two pieces of information, one from the eyes, one from the hand. Okay, now I'm going to ask you questions about the judgment you're going to make about what the size of this object is. And the question is, if I could measure the noise in your eyes alone, noise visual, noise in your hand alone, proprioceptive, does your estimate combine these two noises to give you an estimate that is in between and with a variance that's smaller than either of them? Meaning that if I have X, which is the width of this object, and I have Y vision, and I have Y haptic, that I can measure it. Do I combine YA and YV using maximum likelihood, this generative model based on the noises that are actually present? And that's exactly what they did. That's what they showed. They showed that if my haptic measurement gives me a distribution that looks like this, if my visual measurement gives me a distribution that looks like this. So you see, I drew the Gaussian there with a small variance, right? So now if I wanted to combine them, the combination of these two sensors is not 1/2 YV plus 1/2 YH, because I have much more certainty in YV. So the combination of this is here, and it looks like this. This is X hat ML. So you notice two things. First, my estimate of X hat is closer to YV than it is to YH. Second, you notice that the variance of XML is smaller than either of those two. So my certainty about the actual size of this object is better if I could see it and I could feel it than either of those two by itself. Does that make sense? Okay, so, I hope you get to see how if you can think mathematically, you can do clever experiments, and those clever experiments can generate ideas. And so this comes from the simple notion of how do I combine sensors? Well, you have sensors in your body. Does your brain combine sensors mathematically in a way that makes sense? Does it know the noise that it has? And that paper suggested that it does. Okay, any questions? Yeah.
Like eyes, two eyes, two sensors, visual sensors, right? So I wonder if there's any like studies that did this sort of estimation over one eye versus two examples.
Yeah. We definitely have a preferred eye because if you do that, it jumps for one, but not the other. And so you have the sense of there's the dominant eye. Whether that eye actually sees better or not, I don't know. It's variance enough. But I think there is this evidence that you tend to have a dominant eye. Okay. We were going to hear from you about how to do derivatives of ReLU functions.